The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Okay, so this particular research was done by Musharraf Hussain. So he completed his master's just recently, and he was supposed to be the presenter, but he just got a job as a structural engineering training in Stantec in Victoria. So he did some experimental work. So I'll be discussing about his work on seismic repairing of a seismically damaged bridge column with low-grade GFRP material. So I'll not go into the background. You know about the seismic hazard and its associated damage. And this particular research is mostly for columns, how we can improve the performance of columns. And confinement is the best way. And you know, from the previous presentation you have seen, like already we talked about steel jacketing, concrete jacketing, ECC jacketing, FRP jacketing. Those are kind of passive type of confinement. We can also have some active type of confinement, for example, external pre-stressing or SMA spirals. So, but here we are talking about some passive confinement using glass fiber reinforced plastic. So these are some pictures for external pre-stressing, concrete jacketing and FRP jacketing. So here in this particular case, the research question is, we have, GFRP is obviously cheap compared to carbon fiber, but there are also different types of GFRP available, and some are non-structural grade. Now the question is it possible to use non-structural grade GFRP, which is extremely cheap compared to structural grade GFRP? And the idea of having this research is in BC, in the Okanagan Valley, there are more than 40 different composite companies from medium to large, and they use GFRP for various purposes, for automobile industries, for boat manufacturing, and also for slide, water slide producers. So there are many different companies. So and they want to see like whether this kind of material that they use in their industry is applicable for structural repairing or retrofitting. So that's the intention. And so this is showing like structural grade FRP composites, and we are talking about GFRP. And here in this particular case, for retrofitting, we use bidirectional oven rubbing glass fibers, and we use polyester resin and methyl ethyl ketone peroxide as catalyst. So what does FRP confinement does, we obviously know, and our ultimate goal is it will be performing similar to this, like other standard GFRP. But before we proceed, we wanted to see its mechanical strength. So we tested various coupons, and also when you are doing the confinement for regular GFRP or other CFRP, there is a particular overlap that you have to do, particular length. So we try to see different overlap and see how much strength it can be achieved, whether we can achieve the full strength with larger overlap. And then we also tested for different layers of GFRP. This is for 1 layer, 2 layers, and 3 layers of GFRP. And this is showing the overlap length. And we see that after 150 millimeter, it's kind of, flatten out. So 150 millimeter you can consider as an optimum overlap length. And since we are talking about retrofitting or repairing, we are considering older type of concrete, where in BC in particular, there are some bridges that have very low compressive strength, ranging from 22, and some also have 32 MPa strength. So we wanted to see for very low strength concrete, when you do the confinement with different layers of GFRP, how much improvement you can get. And then we tested with different confinement layers, 1 layer, 2 layer, and 3 layer, and you see that here this is the original concrete, right? This is 22 MPa, and with 1 layer, 2 layer, and 3 layers, you get significant improvement in terms of your capacity and as well as your ductility. So, and if you look into the strength, then you see that this was the control for 22 and 32 MPa, and you get significant improvement with 2 layers and 3 layers. And these are the failure modes that we observed. For 1 layer, there's a gradual rupture of FRP, the similar thing. But when you have 3 layer, there was sudden rupture, as you expect, and also there were distortion under compression. So from here, from the preliminary results, we found out the strength, mechanical strength, also the overlap length, as well as how they will behave and how many layers we can use. And we found that 2 layers of GFRP should be optimum to use. And then we go to the reduced scale testing of bridge piers. So this was the bridge pier prototype, and then we scaled it to 1/3, and these are the test specimen dimensions. And then after that, we also prepared the rebar cages and cast the concrete, and then we targeted for very low strength concrete. So the concrete that we end up was 35 MPa. So we observed the also we tested the coupon for tensile strength, and then our setup was ready for doing the testing. So this was the test setup where we followed the standard loading protocol. The initial stage before yielding, it was 5.1 millimeter per minute, and next we increased to 15.3 3 times. So this is the test setup showing. And so here in this particular case, I should mention that we had 3 specimens. One was control, and then the control one, we tested it, and then we damaged the column, and then we repaired it with GFRP. And we had another control column. So before testing, we retrofitted it with GFRP, with the same materials, same number of layers of GFRP. So then after the testing of the original control specimen, so you had significant spalling of concrete, and you had bar buckling. And then what we did before we start repairing it, we removed the damaged column. We had to provide support so that it doesn't fall. Then we did the concrete grouting, so we repaired it, and then we started. Okay, after this one, then we repaired with GFRP confinement. So this is the deficient pier. We tested. We could test it beyond 4%, and after that, you had significant buckling of rebar, and then it could not take any further load. So it's a significant reduction in the stiffness as well as load. And then this is the repaired pier with GFRP. It shows very stable hysteresis loop, and you see that the capacity was keep increasing. So we actually could not go beyond this one because it is going beyond our stroke length of the actuator. So this was the repaired specimen, and this was the retrofitted specimen. And what we observed, that both specimens almost performed very similarly. Although this one was repaired, and although the bar buckled and everything, so we did not do anything. Just we put some additional stirrups, because some of the rebar stirrups were actually fractured. So we added some rebars, and the bend bars we pushed it inside, right? And just then put the concrete patching and GFRP repairing, and then they were performing very similarly. And these are the backbone curves. So if you look into the deficient pier, this was the capacity, and the capacity was, we said, more than this, because if you had larger stroke length, like it was keep increasing. So we saw like more than 25% increase in capacity, and this one maximum it was 4% drift, whereas it could go even beyond. So 73% increase in the drift capacity. So we also observed the strain response of all those columns, and we also observed the moment curvature response, and we found that the curvature ductility, displacement ductility all increased significantly compared to the deficient pier. And we also observed the energy dissipation capacity. So obviously they went larger drift and they could dissipate much larger energy. And we also observed the residual drift and the repaired and retrofitted specimen. In both cases, you see that they are almost identical. And this is the failure mode of the repaired pier and the retrofitted pier. In both cases, under compression, they were showing some sort of distorted GFRP. As you know, that under compression, FRP is not that strong. And then the repaired pier, there were a little bit of fracture at the end, and it's not because of the reason is at one point there was a little bit of sharp way of when we did the formwork, so that had a stress concentration. If otherwise it would not have experienced rupture at this point. So with that, what we observed that the non-structural grade GFRP can be utilized for seismic retrofitting, and we did not do any durability test because since they are already used in boat building and water slides, where they use lots of salt water, and the boats are already used in the ocean. So in terms of that durability, it should be fine. And from structural point of view, load capacity as well as drift, they give excellent performance. And what we also observed that if you have a bridge that is seismically damaged, then that bridge you should not demolish it for new construction. Obviously, you have to look into the overall damages. If it's only the column, if you can just jack it back to its original position, then with this FRP retrofitting, it could perform almost like new. So, and that could lead to more sustainable construction. So with that, I conclude my presentation. Thank you. And again, this research was funded by NSERC and UBC.